So, this is the third lecture. Stability of structure. Let us briefly recapitulate what we have done in the previous class. So, we have introduced the concept of stability, and the first lesson that we have learned is that in order to analyze the stability, the system must be perturbed. We must be looking for an alternative configuration, right. So, while evaluating equilibrium, we were trying to minimize the potential energy. Here we have to explore the higher order derivative of the potential energy function. Okay. So, we have considered a 2 degree of freedom system and we have demonstrated that how we read into the equilibrium path for the system, and then what is the nature of equilibrium, whether the equilibrium is stable, unstable or neutral, and the approach we followed that was the energy approach. Okay, energy approach we have learned in other courses as well, right. One such example is of course the finite element, in which in order to derive the equilibrium equation, the systems of linear simultaneous equations or systems of equation are derived using minimization of the potential energy functional. So, why we started with the potential energy functional? Because it is little I think easier and most intuitive to master the concept of stability. Okay. So, that was the reason. So, what we have, you can recall that the system that we have considered was consisting of two rigid bar system, right, and they were connected to each other by a rotational spring. At the end also they were connected to a rotational spring, and it was subjected to axial load, compression load P, and these were all dimension L by 2 L by 2, and they were, I mean, for simplicity we assume the identical rotational stiffness for both the rotational spring, right. So, we have derived the potential energy functional pi, which is strain energy minus work done, and in order to obtain the equilibrium path we have made this we have differentiated with respect to the degrees of freedom theta I. So, we perturbed we have perturbed. So, theta I is nothing but when we perturb the system, these were the degrees of freedom basically, right. So, this is theta 1, this was theta 2, right. So, we have in the perturbed configuration we have written down the potential energy functional, and in order to find out the equilibrium path we obtain the the gradient of the potential energy functional, and then for the stability. So, this was giving us the equilibrium path. So, we have obtained the critical load, and then we have considered the higher order derivative of this, right, and there basically we have tried to make it greater than is equal to greater than 0 for stable configuration. For searching for stable configuration, if it is 0, then it is neutral equilibrium, and if it is less than 0, it is unstable configuration. So, this was leading us to the Hessian matrix of the potential energy function, right, and we have investigated its determinant of this, and its principal minor must be greater than 0 for stable equilibrium. Okay. So, by doing so, we have also learned that potential energy functional gives us all the information of the equilibrium path, and then the critical load, and whether the configuration is stable or unstable, and we have also seen the influence of imperfections on that. Okay. Now, other than that, we have also seen that when we are finding out the critical load, we obtain the we obtain two sets of legitimate bases for each, because these are 2 degree of freedom system. We obtain 2 critical load, and respective critical load is associated with a with something called something analogous to mode shape. We call them buckling mode shape, and those buckling mode shapes serve as legitimate basis. So from the physical coordinate theta, we can go to a uncoupled coordinate. So this is the physical coordinate, right? Physical, degree of freedom, and we can we can go to an uncoupled degree of freedom, uncoupled uncoupled coordinate or degree of freedom, right? And thereby we have also seen that the potential energy functional pi, that's what consisting of the terms like theta 1, theta 2, and the cross term like theta 1, theta 2. Whereas when we are transforming this using linear transformation, because these are nothing but eigenvectors, right? So they form a legitimate basis. So potential energy functional become a function of theta 1 and theta 2 only, and we have seen that y1, y2 only, and then potential energy functional for this simple case we have seen that it can be expressed in terms of quadratic term, quartic term, or even higher order term like sixth order term, eighth order term, because all are odd event terms, right? And if we do not require to find out in that case in the Hessian matrix or a determinant or principal minor, rather by looking into the coefficients, sign of the coefficients of the potential energy function, and we can comment on the nature of the equilibrium, whether it is stable, unstable, or neutral. So what we didn't see in this example is that we didn't consider the post buckling behavior, right? We have only considered the critical behavior, not the post critical behavior, and we have also not investigated the nature of imperfections. What is the influence of imperfections on its stability behavior? That we are going to consider using simple system, okay? But this was just an illustration, just to introduce to you the concept of Hessian of the potential energy function, and how various metrics of it, such as determinant and principal minors, are helpful to ascertain the nature of equilibrium, okay? Now onwards we are going to consider simple system, okay, and their behavior to show important insight about the stability of system, okay? So now you may wonder that why we are considering only this simple system, okay? So rigid bar connected with spring, that means rigid system with concentrated elasticity. Why cannot we directly jump into structure like maybe column, maybe plate, maybe cell, or things like that? We can definitely do so, but please you have to be patient, okay? Because using simple system we are going to demonstrate the different class of behavior, okay? And when you do, this is the age of finite element, you see all the thing, skill sets, analytical skill sets what people used to have, perturbation, perturbation, theory, and then asymptotic expansion, different kind of approximation to solve the equation, and now all everything has gone into finite element. You take a commercial software and you start analyzing stuff, okay, knowingly or unknowingly, okay, and in the process you do mistake, okay. So since we can do that using finite element, but understanding and interpretation of the result is more complicated, okay. So that's what I will try to demonstrate, the physics of stability that is we need to learn essentially, okay. So for that we are going to consider several simple system which will essentially demonstrate the physical aspect of stability, okay. So we are going to classify the behavior of all elastic structural system into 4 category, okay. So I am going to show you to 4 simple system, and all these systems are single degree of freedom system. That means their motion or their deformation can be essentially described using a single variable, okay. So what are the 3 different system? This I will call them as toy system because they looks like toy, okay. So I am going to consider first a rigid bar, and this rigid bar is connected with a rotational spring, right, and which is subjected to a load, concentrated load P, and maybe this one is of length L, and the rotational stiffness has a rotational stiffness of C, okay. So that means this is related with C into theta. If this is going to is experiencing a rotation theta, then M is equal to C into theta, then the moment developed is, okay, C is the rotational stiffness of the spring. So this is one system. Next system I am going to consider is like this. It's a rigid bar connected with a spring here, and then it is attached to a spring, okay, and this spring is allowed to to displace it is subjected to concentrated load P. This is length L, this is maybe stiffness K. So this is like a roller kind of support. So that see, this is this system you can perturb it, right? Okay, and here this system also you can perturb it, because if you perturb in this way or that way, this has to be flexible, this has to move, right? So this is a rigid bar which is hinged at one end, and other end is connected with a spring, translational spring, right? This is the second system. The third system we are going to consider is once again a rigid spring, a rigid bar which is connected to a spring and which is subject to a concentrated load P once again, but it is attached with a translational spring, with a restrained by a spring, and this is, but that is inclined spring, okay, and that is free to move on a inclined plane. So that means this is having, so that means this spring is hinged at one end, and other end it is restrained by inclined spring. So this inclined spring has important implication that I will show you, okay. And the fourth system I am going to consider is 2-bar truss, so maybe something like this, this is called Mises truss, okay. These are all hinge, okay. This is a truss, these are all hinge. This is a hinge joint, this is a hinge joint, this is hinge subjected to concentrated load P. This is length L, this is length L, okay, and this is maybe this is a truss member, okay, and here it is. So this is called Mises truss, okay, Mises truss, and these are all. This is a rigid bar connected to a rotational spring subjected to a load P. This is rigid bar connected to a which is hinged at the bottom and connected to a translational spring with horizontal orientation. The rigid bar which is hinged at one end, but it is connected with inclined spring, right, which is free to move at the surface, because when it is going to deflect, it should be free to move. The other one, the last one, is basically truss member. This is a truss member, okay, and subjected to load P, okay. So all these four system, this simple system 1, system 2, system 2, all these four system can display the stability behavior, and all the elastic structural system, and to certain extent elasto-plastic structural system or inelastic system will follow the will demonstrate or display the similar stability behavior, okay. So please note that all elastic structural system, structural system will all elastic structural system, all elastic structural systems, behavior, stability behavior rather, just stability behavior is it can be analogous to any one of the system, any one or in combination of this system, of these apparently simple systems. Please note that. So, 4 classes of behavior we are going to see, clear? So, you understand why, because you shouldn't get bored that okay, what the hell we are doing. This too simple system, rigid bar only and only 1 degree freedom, and associated with the idealized spring, but the importance is that this will reveal a greater picture. That means all the stability behavior essentially is demonstrated by this system in combination or alone will show you the behavior of the real structural system. Real structural system means it is either buckling of column, buckling of beam column, or buckling of plate, or not buckling only, post buckling as well, and then buckling or post buckling or post critical behavior of cell, and nowadays there are other systems as well, nano systems, nano micro systems where the stability behavior are harnessed for the fabrication, for efficient devices and things like that, okay, for adaptive behavior. Okay. So with this thing we are going to start analyzing stability of each one of these, right. So first let us start with the first system, okay, and here we will see what. So what we are going to study? We are going to study the fourth thing. We are going to study equilibrium path, equilibrium path. We are going to study critical load. We are going to study stability behavior, We are going to study imperfection sensitivity. We are going to study stability diagram. We are going to study potential energy functional. Potential energy functional. Please see that all these are the things which we must study, and then it's their behavior. So here first we are going to obtain equilibrium path, then we are going to find the critical load, then stability behavior, imperfection sensitivity, stability diagram, and potential energy. The nature of the potential energy functional and how we can comment on the behavior of the system without going into detailed analysis. Clear? Okay. So for this system, in order to find out, analyze its stability, what are the first things to do? The first thing to do is I am redrawing the figure here. Okay, so here this is a rigid bar. Okay, rigid bar, right? And this bar is connected to a rotational spring and subjected to load P, and so rotational C and length L. So what is going to happen? So you see we are perturbing it. So it is going to go here, going to go there, and then I am basically I am going to, this angle is theta. I mean in any direction, it can be irrespective of any perturbation, can be anti-clockwise and clockwise. And then please note that because it is rigid, but load P is going to remain always vertical, right? It is not going to follow the deformed things. Okay, so this can be, perturbation can be any one of these directions. That's not doesn't really matter. So what is going to happen? This fellow is, if it is theta, then there will be moment develop, resisting moment, and then this fellow is going to do some work. So what is that work? This is the delta. Load. He will do work by deforming this, right? Going. So if you see potential, first we will assume that it's a perfect system. First we are going to study the perfect system. Perfect system, that means no imperfection. Perfect system, that means no geometric imperfection. No imperfection. If we want to put imperfection, what we would have done? We would put little initial rotation. That we are not going to do. Later we will study. So then, potential, we will follow the energy approach. Follow energy approach. So let us find out the potential energy. What is the potential energy? So potential energy is what? Strain energy minus work done. Okay, strain energy is C minus work done. So strain energy will be what? Of course, you see that half moment into rotation. So, half m into theta, m is nothing but c into theta. So, half c into theta square, right, half c into theta square. And what is the work done? Work done is this p into delta, and this delta is nothing but what? If this is length L, this L cosine of theta, and this L into 1 minus cosine of theta, right? Fine. Now, one thing I can do, okay. So, when I am doing that, I will first find out equilibrium path, right? So, from there, what I am going to do, del pi by del theta must be equal to 0 for the equilibrium, right? So, del pi by del theta is how much? C into theta, right? C into theta minus P into L, cos theta is sin theta is must be equal to 0. So, P must be equal to C theta by L sin theta, or C by L theta upon sin theta. So, the equilibrium path is nothing but equilibrium path. So, you see, if equilibrium has to be satisfied, of course, theta is equal to 0 is a fundamental path, because that is without perturbation, right. It will always remain in equilibrium, theta is equal to 0, right, but we are going into alternate configuration, right. So, that is for non-zero theta. So, that will be what? The equilibrium path will be given CL theta by sin theta, right. Now, I am going to draw it. How it will look like? Okay, then this equilibrium path, now I will find out the critical. So, what is the critical? Stable, unstable, second order derivative we have to find out, right. Critical means transition between stable to unstable, right. So, the critical load, if we want to find out critical load, right. So, what we are supposed to do? Let us differentiate double del 2 pi del theta 2 is how much? Del 2 pi del theta 2 is how much? C minus C L cosine of theta must be equal to 0. So, P critical is nothing but C divided by L cosine of theta. So, C by L 1 by cos theta, right. This is the critical load, clear. So, what we can see that at theta tending to 0. So, when theta tending to 0, theta tending to 0, cos theta is what? If theta C by L. So, until and here theta tending to 0, theta by sin theta is what? Limit theta tends to 0, sin theta by theta is 1. So, C by L. So, until C by L, it will, until C by L, it is fine. This is stable part, but after that it has to bifurcate, right? Because then for theta is equal to 0, it is not a stable path, right? Not an equilibrium path even. So, it has to have some deflection, and that equilibrium path is given by what? C by L theta by sin theta. So, how it will look like? Theta by sin theta. Of course, this is a curve, right? Now, you know this identity, right? You all of you know this identity, theta greater than sin theta less than tan theta. When you are in first year mathematics, differential calculus, you must have done this theta when expressed in radian, and this identity, this inequality theta greater than sin theta less than tan theta for all theta, you know that. So, that means theta by sin theta, theta for any theta, it is always what? With increasing theta, it will increase, right, that ratio. See, when theta tending to 0, theta will be sin theta, but as theta is increasing, theta will be much higher than sin theta. So, it will be a increasing type of, so it will look like something like this. You see that? It will look something like this. Are you understanding? And then it's symmetric. It is symmetric, right? So, what we see that my path was that this was the fundamental part. After that, it is bifurcating, right? Clear? So, this is my critical load, and then P is basically critical is nothing but P critical is nothing but C by L here this point, and then the equilibrium path is here what we are plotting, C by L theta by sin theta. So this path is nothing but equilibrium path, and we don't know till now that whether it is stable or unstable. We will see there. Clear? Okay. Now next thing, that if this is the equilibrium path, we have to see the nature of equilibrium path, whether it is stable or unstable. Okay. So how to do that? Okay. So to do that, what we will do, let us preserve it as the potential energy functional. We will do that later. So see the post critical path, we want to see. So for that, what we will do, so for so the stable and unstable, so del 2 pi del theta 2 is nothing but C minus PL cosine of theta, right? This is nothing but stability path, right? Because that will decide if it is 0, then it is boundary, greater than 0 stable, less than 0 unstable. But please note that on the top of it, the equilibrium must be satisfied, right? We want to study the stability of the equilibrium path. First, the system has to be stable, has to be in equilibrium, right? So equilibrium condition must be imposed on this, isn't it? So for that, so this is C minus, and this P is what? C by L theta by sin theta, then L cosine of theta, and this is nothing but C minus C theta by tan theta, so C 1 minus theta by, or I can write, I will just simplify it, del 2 pi del theta 2 is equal to C 1 minus, if you want, theta cot theta. Now I will tell you something. Look, what is the inequality? Theta is greater than sin theta, less than tan theta. So theta by tan theta is what? Theta by tan theta less than 1. That means this is always greater than 0. For always for all theta, for theta, always for theta not is equal to 0, That means my post critical path, that means this path is what? Stable. So my post critical path is stable. So this is a stable path. This is a stable path. For all theta, this is a stable path. All of you understood, right? What? One more information I would like to give it to you, that whether what will happen at theta is equal to 0. Theta is equal to 0 at theta is equal to 0. See, at theta is equal to 0, theta by tan theta is 1. So del 2 pi del theta 2 is basically what? C 1 minus 1 is basically 0. So that means at theta is equal to 0, you don't know the configuration. Theta is equal to 0 means when PCR is equal to CL, this is the critical load. You don't know the nature of nature of equilibrium where P critical is reached. Just so for that, what will you do? We have to look into the higher order, the way you did when you did maxima minima in your using differential calculus. So what we should do? Okay, let's do one thing. Okay, del 2 pi del theta 2, del 2 pi del theta 2 is nothing but C 1 minus theta cot theta, and is equal to C 1 minus theta. What is the expansion of cot theta? The cot theta expansion is nothing but, I am writing it 1 by theta, 1 by theta. You can do Maclaurin series expansion, minus theta by 2, theta by 3, minus theta cube by 45, minus theta cube by 45, and higher terms if you want to include minus 2 by 945 theta to the power fifth minus 2 by 945 theta to the power fifth, and so on. I mean, okay. So, this I am going to 1 minus this will theta will go 1 and then minus plus theta square by 3 and then theta to the power 4 by 45 and whatever. Okay, I am going to neglect all these things. So, this will go. So, I am going to write C and then theta square by 3 plus 3 to the power 4 by 45, and things like that, whatever. So, what I will do then, let us first then, so from here I am going to come here there. So, del 3 theta del theta 3 will be 2 theta by 3 plus 4 theta cube by 45, approximate. Please note that this is approximate, right? Once again, this you will not be able to decisively say that what will, because all this contains theta. So, when you put theta tending to 0, this will all be 0. You take further derivative del 4 del theta 4 2 by 3 plus 4 by 44 3. Now, you see that there is some constant term plus square all this term. So, that means if other terms also vanishes, but this 2/3 will stay. So, that means theta to the power 4 by theta to the 4 pi by theta d theta 4, that is greater than 0. That means the critical load, that means at critical load, that means, so the critical state is stable. So, that is stable, that means critical load critical means C by L, right. So, what we can see, that the stable fundamental path at theta is equal to 0 goes and bifurcate into, it results into a stable critical state, and then subsequently it bifurcate into a symmetric stable path, which is theta non-zero, symmetric stable deflected, and then an unstable fundamental path, because here this is broken line is unstable, because when the load is greater than C by L, this cannot be stable anymore, right? It has to deflect, right? So, I am just writing something. So, this statement you must try to understand. So, I am writing down something. So, when you will not be able to find out using lower derivative, then you should go for higher derivatives. Okay, please note that. So, I am just writing that stable fundamental path, fundamental path that fundamental path is nothing but theta is equal to 0, bifurcates into an unstable equilibrium path and unstable equilibrium path for the given state configuration of the bar, for the state configuration of the bar State means configuration, that means theta is equal to 0, right? Configuration is theta is equal to 0, unstable equilibrium path, and a stable post critical and a stable post critical equilibrium path corresponding to deflected configuration, deflected or perturbed configuration, that means theta is equal to non-zero, which theta is equal to non-zero. Okay, is fine. I am reading it out, please note. Stable fundamental path theta is equal to 0, bifurcate into an unstable equilibrium path for the straight configuration theta is 0, and a stable post critical equilibrium path corresponding to the deflection configuration. This was stable, this is bifurcating into a stable path, this is unstable. Clear to all of you? Now, so what we have done? We have obtained the equilibrium path, we have obtained the critical load, we have obtained the nature of the equilibrium, nature of the stability of the equilibrium path. We have demonstrated that this system demonstrates a stable path, right? Stable post critical path, because load is increasing, as theta is increasing, load is increasing. The kind of system which shows this kind of behavior is basically buckle column shows this kind of behavior, although very little post critical strain. See, like buckling doesn't mean that the load carrying capacity is depleted, eliminated completely for the system. Post critical stage also that structure can carry load, but for column, so very little post critical load, very little, for 30-degree deflection, it can only have 4%, 5%, increase in load. But for plate, it is significant. So this kind of behavior is portrayed by column and plate. Okay. All of you are learning plate theory, right? Another thing, what is important here, I would just try to write this potential energy function, which I just, this is a potential energy function, right? So if you expand it, how does it look? So what do you see? That potential energy function becomes a function of what? Theta square, theta to the power 4, theta to the power 6. Do you see that? So it's a function of all what? Quadratic term, quartic term, and then others, right? All are even terms, right? There is no odd order terms. So this is a very important, very interesting, and if you substitute over there, then you will also see that equilibrium path P, it remains same. So this is a characteristics of the system which shows the symmetric bifurcation. Whether it is stable or unstable, that is a different matter. But symmetric bifurcation a system is essentially characterized by these even terms in the potential energy functional. So by looking into expression of the potential energy functional, you can comment on the stability behavior of the system, And that is what nowadays if you see ion, that what is the concept this Hutchinson's, that the energy landscape theory, I think when you are qualitatively constructed that using probing load technique, you can essentially fit a functional like that. Okay. So, a system by looking into this functional expression, you will be able to comment on the stability behavior. So, I will see now. So, you understand the nature of the potential. Now, I will just put little little imperfection in that. Okay. So, if I want to put little imperfection P, and then maybe here I am assuming that this is having some imperfection alpha. Okay. And then further I am just pushing it, okay, theta. And this is P, this is P, this is L. Okay. So, what will be the potential energy functional? Pi half C theta minus alpha square minus PL cosine of alpha minus cosine of theta, right? Isn't it? Once again you do all these calculations, equilibrium path del pi del theta is equal to 0. I am not doing it, but I am writing down the expression. That will be equilibrium path will be C by L theta minus alpha by sin theta. Alpha is the imperfection. Okay. And then this equilibrium path, and you will also see the critical load you can find out. So, critical load will not depend on the imperfections. So, it will have the similar expression as you earlier, but now we want to find out the stable or unstable nature of stability, right? Nature of equilibrium, higher order information, nature of equilibrium, equilibrium path. So, that if you write del 2 pi del theta 2, then this expression you will get C minus C theta minus alpha what theta, and from there you will see for stability, so the condition for stability, this must be greater than 0 for condition stability, condition of stability, stability is basically that this, if you simplify, tan theta must be greater than theta minus alpha, right. So, now it is not only theta that is important, it is also alpha that is coming into picture. Look, equilibrium path depend on alpha, but critical load does not depend on alpha. However, the stability condition, stability boundary will depend on alpha, the magnitude of imperfections, right. So, how I will draw that? So, if I want to draw that, I will draw on the top of it, I will superimpose that here, and the way it will look like, this look like a flowery picture, you see that, how I am going to do that, you see please. what I am trying to show you, please note that. Okay. See what I told you, that when there is imperfection, the imperfections basically destroy the bifurcation path. See, if you see the main diagram was the stable fundamental path is bifurcating into stable these two, right. So bifurcation was occurring. When there is imperfection, see this is alpha greater than imperfections, so path there is no bifurcation, but please note that this path is drawn in a way so that one of its ends are asymptotic to the equilibrium path. You see that? So the equilibrium path of imperfect system asymptotically approaches to the equilibrium path of the stable system. Do you see that? So please, I am writing it down here, please note. So you have to take different value of alpha and you have to plot. So what the alpha value will take? 0.01, 0.02, 0.03, something like. So you see that. So the equilibrium path of the imperfection system system asymptotically approaches to the perfect system, to the equilibrium part of the perfect system, okay, to the equilibrium path. So that is see, it destroys the structure. So incorporation, look, please note the diagram here. You see, this is the perfect structure and these are the equilibrium path for the imperfect structure. These are all stable. So all the solid line are stable, all the broken line are unstable, and this particular, where there is this particular is the stability boundary, because this basically defines the stable and unstable boundary. So that's what you see, that I have broken line here, you see that, and here also this this limb of the equilibrium path is asymptotically approaches towards theta is fundamental path. Do you see that? And fundamental path itself was unstable. See that this was unstable. These are all, even imperfection system are also unstable, and they are approaching towards this unstable fundamental path. Theta is equal to 0. You see that? Whereas beyond reaching critical low, this was a stable path, and after bifurcation it is a stable path. Imperfection system equilibrium path is approaching them asymptotically. You know what is an asymptote, how to find out asymptote, right? And these are for different imperfection, alpha greater than 0, alpha less than 0. Now in the top, these are basically reversed. This is alpha greater than 0, alpha less than 0. Now you may wonder that how I am obtaining this. You put some numerical value, and if you plot the you use some plotting software, and then you plot it, you will get the same thing. Okay, take typical value of that. Okay. But one important thing you must understand, that stability and instability, stable and unstable are separated by the boundary, and this is the boundary over which del 2 pi del theta 2 is 0, right, because that's where from stable to unstable. You see that from here it is stable, solid line, but here these are all broken line. You understand the unstable to stable transition boundary? That's what I am defining at the stability boundary. Clear? One more important stuff that I am going to explain it to you is that you see how you are obtaining the stability boundary by the making the Hessian or by second derivative to be 0, right. There is another way we can obtain it. You know how? You see that stability also implies that these all are having, okay, let me explain it here. So, this the condition of stability, you are getting something like this, right, here stability boundary, right. Could you please give me the equilibrium path? Equilibrium path, what was the expression for the equilibrium path? Equilibrium path was C theta minus alpha L sin theta, right. C theta minus alpha L sin theta, right. You see, I will just do one thing. So, P equi by del theta you see that 1 by sin theta 1 by theta minus alpha cot theta. You see this is analogous to this C 1 minus theta minus alpha cot theta. These two expressions are analogous, only the difference is that there is sin theta. So, now the equivalence between this and that expression you can understand, right. So, what I can say that del 2 pi del theta 2 is analogous to del P equi by del theta, right. Then see, when you differentiate once again, see, for ascertaining the stability boundary or stable and unstable transition, you have to explore on the second derivative of the potential energy function, right. And when you are doing that, when you are obtaining del 2 pi del theta 2, then on that P you have to impose the equilibrium path as well, because see, the first system has to satisfy equilibrium, right. So, finding out del 2 pi, see, for this system it is simple, because that is what del 2 pi del theta 2 you can easily find out. But for complicated system, you will see when this toy system there will be a problem to establish. Instead of that, whatever the equilibrium path, if you take the derivative of that, that will be analogous to this. So, that will also reveal the information. Now, could you please tell me why this and this are same? I mean, these are kind of equivalent. See, how in finite element what you did, in order to find out the equilibrium equation, right, when you obtain the matrix equation, assume that I mean you have considered linear finite element, right. In linear finite element you have minimized the potential energy and you get sets of linear simultaneous sequence, right. Now consider, so that was the way you obtain, right. Now consider it's a nonlinear system. In nonlinear system, what do you do? How do you analyze nonlinear system? You don't write the equilibrium, you write the equilibrium in the incremental form, right. So, instead of making the potential energy minimization, you just incremental potential, okay, delta pi is equal to 0, right. So, in incremental, you write down the equilibrium in incremental form, okay. Then incremental form, that leads to what? That leads to nothing but, you just give, and I mean you can write down the same incremental in two different, of course, one is energy, but in nonlinear finite element it is easier and convenient to write down in what? In using the virtual work, okay, because virtual work equation is more generalized. In many cases that this energy minimization might not work. especially in there are some nonlinear systems where it will not work, and sometimes you must have learned that instead of potential energy functional you sometimes work with the complementary functional, and this, and there are many functional alternative functional that people have proposed. But when you write down virtual in virtual, if you write virtual equation, right, but using virtual work, right, then you basically whatever the equilibrium, you just you apply some virtual displacement and you write down the virtual work equation, right, and that give you incremental equation, right, incremental equilibrium equation. So see, in linear finite element, what you have obtained? You obtain the force is equal to stiffness into deflection, right, and incremental, if you want to write, then you are going to write delta p, this I am going to write f, okay. So I am going to write delta f is equal to kt into d, I mean I am going to write here instead of delta I am going to write u. So here it is, I am writing delta u or du, right. Here basically you see these are the what forces and this is displacement, right, k is equal to k into linear finite. In incremental form, these are the internal forces and these are the equilateral deformation, and this is tangent stiffness matrix, tangent, right. So when you so this is what dpq by delta theta, this is nothing but this will give you what, nothing but kt, tangent stiffness matrix, okay. The equilibrium, so first order equilibrium you have obtained, right, equilibrium path, but now you are differentiating further. That means what will happen if there is little change in theta, what is going to happen in the internal in the p, okay. So that is del eq by, so both of these, whether it is Hessian of the potential energy functional or it is the gradient of the force with respect to theta, both are equivalent simply because they corresponds to a incremental equations, okay, incremental equilibrium equation, and they basically ascertain the determinant of kt, the tangent stiffness, okay. I will explain it here. You see here why it is stable, because you draw a tangent here, tangent is always positive, del theta is what, nothing but tangent stiffness, right, it is positive, positive means what, you see that, because here it is scalar, right. If it's a multi-dimensional space, multi-degree freedom system, you have to take, of course, determinant and principal minor. Positive means it's stable, these are all stable. See, in negative, you said here also for negative theta, in the slope will be negative. So you see, so ultimately del p del theta is equal to positive, okay. So that's why it is positive. There it is positive, here it is negative. That's why it is unstable. You understand that? So slope of the equilibrium path also reveals the nature of equilibrium. Slope of the equilibrium path reveals the nature of equilibrium, whether stable or unstable. Please note it down. The slope of the equilibrium path reveals the nature of stability. Clear? And then the equivalency you must keep into mind, in your mind, that the equivalency of the Hessian and then the gradient of the equilibrium path with respect to the displacement. Yeah, this will come handy, okay. So you see this flowery diagram, it reminds you maybe I don't know what, it reminds me something else, in biology what you have, then when you used to cut this flower, right, you see that, and then you will see that you will remove the petals, right, and then you will see that, I think then there will be egg, and then these things will come and then fertilization, etc. So it reminds me that figure actually in biology, right, isn't it? Anyway, one more thing is still remaining, the imperfection sensitivity. So you please see the simple del 2 pi del theta 2. We are going to study the last aspect, that is imperfection, and I think it is most important, okay, imperfection sensitivity. And so del 2 pi del theta 2, I have derived it. What was that? That was nothing but C 1 minus theta minus alpha cot theta, right? That was 0, that is the stability boundary. So, I want to study stability boundary. So, from here what you will get, tan theta is equal to theta minus alpha, and this is on the stability boundary. Okay. So, I will just expand this tan theta as theta plus theta over c is equal to theta minus alpha. Okay, and that means theta cube. Of course, this will all approximate, x. So, theta cube is nothing but minus 3 alpha. Okay, this is one equation, right? Now, you tell me that what was the critical load? Critical load was C by L, 1 minus cos theta, 1 by cos theta, right? And I am trying to study the imperfection sensitivity. I will, what is imperfection sensitivity? Imperfection sensitivity is nothing but dependency of critical load on imperfection. Dependency of critical load on imperfection. Imperfection sensitivity implies the dependency of critical load on imperfection. So, why it is important, you will see from here we will generalize our notion of imperfection sensitivity. Coiters back in 1940s, Coiters, okay, he developed imperfection, his theory of imperfection sensitivity. And you see those time there were no finite element, right? Finite element appears only around 1950s or so. I mean, that was, I think, the development of computer and then the development of matrix method, whatever is the precursor of this finite element were similar actually, okay. So, I mean, it, development of computers, digital computer was played a synergistic role, right, in both. So, at that time there were no this, no finite element and things, and all these great minds basically worked, and Coiter was one of them. Of course, initially when he wrote down his thesis, I mean, it was in the German language. So, later it was translated by someone. Who translated it? Can you recall? No? I think, and then he was a, I cannot recall his name, but he told that he has rediscovered Coiter, okay, Coiters. So, Coiter's law of imperfection sensitivity. Because why I am mentioning, because quite sometimes people will think that what I mean a simple system, why I am doing all this unnecessarily mathematical jugglery, I am doing, but that is not actually correct. There are much more interesting thing to do, recently one of my my student, PhD student, has worked on this direction, and then he got a couple of good publication on that. Actually, we have exploited the Coiter's notion in SFT assessment and probabilistic, and imparting what is the influence of random uncertainty on cell buckling and things like that. So, Coiter's basically developed the law of imperfection. I will state that what it. So, these are called power law of imperfection sensitivity. Okay. So, Coiter's, when he discovered, his thesis went into oblivion. So, this was not noted by later people. When it was translated, it got a wider attention actually. Okay. So, from here, see, his treatment was different. I mean, but if we cannot generalize to that extent in classroom setting, but using simple system, we will see, we will lead to those kind of things. Okay. And you will see, you will be able to appreciate that what we are doing. Okay. So, I have seen that, okay, we let us, I mean, we have to get rid of this theta, we have to relate P's here with alpha, right. So, we want to study whatever is going on in the stability boundary, let us. So, in the stability boundary it is 0. So, that basically gives us what? That basically gives us relation with theta gives minus 3 alpha, right, on the stability boundary. I am assuming that theta is small, that because theta is small, that is what, I mean, we can truncate the tan theta within two expressions, right. Okay. So, then I am just writing this CL 1 by cos theta is nothing but sec theta, and sec theta is what? Sec theta is root 1 plus tan square theta, right. So, I am going to write it 1 plus tan is nothing, tan is 3 theta plus theta cube by 3 square half, and then 3 by L 1 plus theta square plus theta 6 plus 2 and here what we are going to do, C by L, neglect the higher these terms, just take one. What is theta square? Theta square, theta cube is minus 3 alpha. So, theta square is nothing but minus 3 alpha, 1 by 3. So, 2 by 3, So, so you can see this we can write as C by L, 1 plus C 1 plus alpha, some constant alpha to the power 2 by 3, right? Some constant maybe some constant, maybe some small some constant, okay, maybe C cap, okay. You say minus 3, when it is square, then it is minus will be plus, right? We can write it like something like this. So, what we can see that P critical, it becomes P critical and this plus. So, what does it mean? The critical load is going to increase with imperfections, and what 2/3 power law. So, this is, so I will now draw the imperfection sensitivity diagram. So, here I am going to write alpha is the imperfection. So, P critical was C by L for, but then this is going to increase. You see that? So, P critical basically it increases, it is being 1 plus some order of some constant alpha to the power 2 by 3. So, this is Quater's 2/3 power law of imperfections. So, a system, which one we do? Okay, well, I mean, you just take it, this series expansion. So, you just take half, okay, binomial, you do binomial, okay. So, that is what, because 1 plus theta square to the power 1 plus half theta square, okay, that is what this half and this all these things I am condense. So, what we see that a system which demonstrate stable bifurcation, and then it potential energy functional contains this all quadratic term, it gives increasing critical load with imperfections. So, imperfections rather increases the critical load, right. So, and that follows. So, this is called Quater's 2/3 power law, Quater's 2/3 power law, but please our law power law. So, this kind of system follows 2/3 power law, okay. So, why it is happening? Why do you think that imperfection is increasing the load? The reason is that if you see, consider the system, it was restoring force is coming by rotational spring C into theta, but the destabilizing force is what? C into L, what? C into L into theta, L into sin theta, right. So, the destabilizing force and sin theta is always less than theta. You see, especially for higher theta, I mean, so theta is equal to 0, sin theta tending to theta. You see, so higher theta, what is happening? Your restoring force is increasing in much a larger rate than that of the the disturbing force. You see, your restoring force of the order of c theta, and your destabilizing force is of the order of sin theta something, okay. And because for theta increases in the larger rate than the sin theta, for increasing theta, the restoring force is being more dominant than that of driving force, and that is what is leading to this not only the stable bifurcation, but also the imperfection sensitivity. Okay. And imperfection, this is called this is not imperfection sensitive. That means when the critical load is increasing, this is called imperfection insensitive, and two-third is not very significant power law. I will come there, worst imperfection sensitive. So this kind of structure, because the critical load increases with imperfection, these are referred as not imperfection sensitive. When the critical load decreases with imperfection, that is called sensitive. But then there is mild sensitivity and worst sensitivity. So two-third power means it is mild sensitivity, and here it is insensitive because it is increasing. Clear? Okay, thank you for today's lecture. Next.